Hello and welcome. I'm Professor Tsuchiya, and I'll be guiding you through this introductory course on using Simulink to simulate dynamic systems. In the previous video, we saw that if you applied a constant amount of thrust to a vehicle, the output looks something like this. We knew this intuitively. We also learned that Simulink requires a mathematical model that captures the system dynamics. Fundamentally, the process of mathematically capturing a dynamic system is called system identification. There are many ways to identify a given system, but one simple way to model a mechanical system like this is to first analyze the external forces and then apply Newton's second law. To analyze the external forces, a free body diagram is extremely useful. Since we're only concerned with the dynamics of the vehicle in the horizontal direction, we only need to consider forces in that direction. There's one force providing a forward thrust, and another aerodynamic drag force, which is often simplified as a proportional gain that scales the velocity. In reality, this is a quadratic function, but a simple linear model serves to illustrate the modeling process here. Then, we can apply Newton's second law to produce the following equation. However, we need to think about this equation as an input-output relationship where the input is u and the output is the velocity v. Thus, our equation should be in terms of these variables. Making the appropriate substitutions, we arrive at the following ordinary differential equation. It's important to pause at this moment to understand what this equation represents. It's a mathematical representation of the dynamic system defined in the free body diagram. In other words, for any given input u of t, we should be able to solve the differential equation and arrive at the actual output velocity profile. Let's use one example to verify our intuition at the very beginning of this video. If the input has the form u of t equals 1, in other words, just a constant value, then the particular solution to the differential equation has the following form. It's clear that when t is equal to 0, the velocity is also equal to 0. Additionally, when t approaches infinity, the velocity approaches a terminal velocity of 1 over b. In between, an exponential function is gradually subtracted and the final velocity profile is shown to agree very well with our intuition. Now suppose the input is something else, like an exponential function, or the Dirac delta function, a sinusoidal function, or any other arbitrary function of time. In order to compute the velocity, you would then need to solve the differential equation for each one of those different cases. Or, you could program the whole system into Simulink and let it run all of the simulations for you in a tiny fraction of the time it would take you to solve the differential equations by hand. This is a fundamental motivation for using a program like Simulink to run simulations. Once you program the automobile dynamics into Simulink, you can run various simulations under different parameters and even under different initial conditions, all at the click of a mouse. All that remains to do is to figure out how to program the model of a dynamic system into Simulink, which we'll do over the next few videos.